Hey everyone, we're going to do lesson 2.6, which is on ground and excited states. And this is going to translate really well into a lab we're going to do in a few weeks. But go ahead. This is a really cool welcome question. What makes you excited? Pause the video, answer the question, and when you're done, go ahead and play the video and we'll get started. So states of atoms is really, it really relies on the arrangement of electrons. So electrons contribute to the states of atoms. So whether those atoms are reactive, whether they're not reactive, whether they're stable, whether they're not stable, this all has to do with where the electrons are and where they want to go. So most of them want to stay grounded, but we're going to learn in a few units or in a few lessons, why that is and why electrons are a little bit, why some molecules or atoms are a little bit more stable than others. And it has to do with their arrangement of electrons. And the first thing I want to define for you is what a ground state is. So a ground state is the sort of, for lack of a better word, the normal arrangement of electrons around an atom's nucleus and really important in their respective energy levels. So this is a ground state, and we're going to talk about where we can see the ground state. We've actually drawn some ground states recently. But this leads us to what an excited state is. An excited state is a temporary state in which the electrons in an atom move from one state to another. From one energy level to another energy level. And usually, this will leave an energy level unfilled. So if we remember, we drew things called Bohr models. And if we review Bohr models, we really worked up to 3 energy levels, but kind of 4. We stopped at 20 electrons. And if we remember correctly, the first energy level can hold up to 2 electrons. The second energy level can hold up to 8 electrons. And the third energy level can hold up to 8 electrons. Okay? So let's go ahead and draw the Bohr model of nitrogen so that we can get some review with this. If we look at the periodic table, nitrogen has an atomic number of 7, which means it has 7 protons. Its atomic mass is 14 We subtract that by the number of protons. We have 7 neutrons. And we're going to assume that nitrogen has 7 electrons because it's in that nice balanced position. So if we were to draw the Bohr model of nitrogen, we'd have our protons and our neutrons in our nucleus. And I'm going to go ahead and draw our first energy level and put our first 2 electrons in there. So we have 7 electrons, which means our first energy level or shell is filled. And we need to add 5 more electrons to our second energy level. Now we have a total of 7 electrons in our Bohr model. This is what I mean by the ground state of nitrogen. The electrons are arranged normally. It has 7 electrons. There are 2 in the first energy level and 5 in the second energy level. This gives us a total of 7 electrons. Now, if we notice in our Bohr model, our second energy level only has 5 electrons, but it can hold up to 8. So what's going on in these little empty pockets here? This is just known as empty space. Okay? And this is going to allow us to talk a little bit about what excited states mean. It means that we can move electrons from one energy level to another energy level. But before we actually do that, there are some ground rules that I want to go over. So kind of when we talk about excited states, it's important to know that, number 1, all elements have only one ground state. And for nitrogen in particular, this is the ground state, the Bohr model that we just drew. Number 2, most elements have multiple excited states. It means that we can arrange electrons in a lot of ways as long as we're not going over the maximum for each level. Number 3, electrons can move from one energy level to another energy level if that energy level is not filled. And finally, we're only focusing on the first 3 energy levels. I won't give you any problems that have to go past that because that involves opening up a d orbital, and we'll talk a little bit about that at the end. So again, let's go ahead and draw our Bohr model of nitrogen. And I'm going to go ahead and draw that super quickly. P7N7. We have 2 energy levels. 1, 2. I'm going to make a copy of this. And we have our 7 electrons arranged in this order. So it is possible for this atom of nitrogen to get excited. And when it gets excited, it's going to allow electrons from our first energy level to go into these to go into an empty pocket in the orbital above it. And when that happens, our nitrogen is going to get excited. And what that means is now the Bohr model is going to look like this. Now, this is abnormal. This doesn't just happen. This only happens intentionally. Something has to make the electron do this. And if we think back to our definition of excited state, it's only temporary. Okay? And there are certain things that can cause the electrons to do this. Okay? So the causes for excited states. And it's really important to say that not electrons don't want to do this. This takes a lot of energy, but really the causes or things that can make excited states happen are, number one, heat. If heat is applied to something, it's going to move those electrons into an excited state. The second thing that can do it is if it comes in contact with an electrical current. A lot of electrons will move positions if they come into contact with electricity because they repel each other so much. Or even collisions with other atoms can cause excited states to occur. But again, these excited states are only temporary. So when the heat, electrical current, or collisions have stopped, the electrons will move or return back to the ground state, where they kind of normally or they're happy to be in. What we want to be able to do is we want to be able to draw what a ground state and a normal state would look like for different atoms. Okay, so let's start with an easy one. I shouldn't say easy. Let's start with one that's fairly simple, and that's beryllium. Beryllium has an atomic number of 4. So it has 4 protons. It has 5 neutrons according to the periodic table. And in this case, it has 4 electrons. So if we draw the ground state for beryllium, we have 4 and 5. That's our nucleus. Let's draw our first energy level and our second energy level. This is what the ground state of beryllium looks like. If we wanted to draw the excited state, we would take one of the electrons from the first energy level and we'd put it into an empty pocket in the second energy level. So now our Bohr model would look something like this. We still have 5 protons and 5 neutrons. We didn't change the element, so we still have 4 protons. We just changed the arrangement of electrons for a second, we maybe applied some heat to it. Who knows what we did? But we excited this beryllium atom. So now we only have one electron in the first energy level, and we have 3 in the second energy level. Now, super, super important. Once the heat or the collisions or the electricity has stopped, it's going to return to its ground state eventually. Let's do another example, and let's look at the ground state and the excited state of aluminum. Aluminum has an atomic number of 13, which means that it has 13 protons. The atomic mass is 27, so it has 14 neutrons, and it has 13 electrons. So again, I'm going to put the protons and the neutrons in the nucleus where they belong, and I'm going to go ahead and draw the excited state as we go through this. Our first energy level, our second energy level, and I'm going to go ahead and draw the third one, just because I know that there's 3. Oops. Okay. Now I have 13 electrons, so I want to put all 13 on the correct energy levels. 2, 4, 6, 8, 10, 13. And again, I have lots and lots of empty pockets that I can fill on this energy level, on this third energy level. Now, we don't want to get crazy. We don't want to move one from the first energy level to the third energy level. We absolutely don't want to do this. This is incorrect. But we can move. What's probably happening is, if we excite this, electrons are moving from the first to the second and the second to the third instantly. But we can't really draw that in particular, so we can just take 1 or 2 electrons and move them from one energy level to another, as long as it's not full. So we can't move. There's lots and lots of different ways that we can do this. Lots of ways. As long as it's different from the ground state. Number 1, it has to be different from the ground state. Number 2, it has to have 13 electrons. Those electrons didn't just disappear. And each ground state must have 1 electron if it's not full. Okay, so I'm going to go ahead and just draw a random one. I'm just going to move 2 electrons from the second energy level and put them on the third energy level. So again, my first one is going to stay exactly the same, but now my second one, I'm going to leave 2 of them out, and I'm going to add them to my third. So I still have 13 electrons. It's different from the ground state, and each ground state must have at least 1 electron if it's not full. So I think I did a pretty good job here. I'm going to do one more example, and I'm going to do neon. Neon has an atomic number of 10. So it has 10 protons. Its atomic number is 20, so it has 10 neutrons, and we're going to assume that it has 10 electrons. I'm going to go ahead and put my protons and my neutrons in my nucleus. I'm going to draw our first and second energy level, and I'm going to put my electrons in their respective energy levels. 2, 3, 4, 5, 6, 7. So what's happening here is all the energy levels are full. We can't just make another energy level. It doesn't have another energy level. There's no empty space or no empty pockets to put electrons. So neon is an example of an element that has no excited state. So just be careful with these. It's really easy to distinguish these. It's all the noble gases. So we went over the periodic families. All noble gases have no excited states. So that's helium, neon, argon, krypton, xenon, radon, and element 118. The last thing I want to go over is we've been referring to the electron paths as energy levels. And this is completely correct. But we're going to go into a little bit more detail on what these are. Like what is an energy level? And it has to do with something called an orbital. And an orbital is like the home of an electron. Orbital orbit the nucleus. In an orbital, something orbits the nucleus. And next time we're going to talk about what's known as electron configuration, and we need to be familiar with the 4 types of orbitals and how many electrons can fit in each of the orbitals. So the first orbital is the s orbital, and that can hold 2 electrons. Very similar to the first energy level. The p orbital can hold up to 6 electrons. And again, I know it's not 8, but we'll make sense of this when we do our electron configuration lessons. The d orbital can hold 10 electrons. And these are special elements that we'll talk about very, very soon. And the f orbital only has to do with the lanthanides and actinides, and these can hold up to 14 electrons. And again, you don't need to know why right now, because we're going to talk about that in our next lesson. You just need to know the amount that they can hold for now until we get more practice with this. Anyways, this is the last of the recorded lectures. Hopefully there is some homework for you to do on the worksheets, and I will be checking your notes, just FYI.